in adaptive optics instrumentation, black hole microlensing, and most recently, physics and astronomy education research. Besides her scientific research, she is interested in developing inclusive and effective pedagogical methods for teaching physics and astronomy, as well as improving equity and access to education in these fields. After graduating in May, she plans on teaching and developing research programs in Oakland community colleges. So, welcome, Fatima. Thank you so much for coming to speak with us. I'm going to go ahead and get us recording. Already was recording.
And just, I should have asked this before, but do I have the ability to make breakout rooms?
I don't believe so, and neither do I.
So you can. I'll
Okay.
do it for both of you.
I'll ask you to
There's few enough of us that we could just have a communal breakout.
Oh, I have a fun thing that works well in small groups, but we'll get to it later. But if at some point you could put people in like, oh, perfect, I'm co-host now, so I can do it. Awesome. Okay, let me share my screen. All right, is my title screen visible? Okay, so hi everybody. My name is Fatima. Today I'll be talking about the most recent parts of my graduate work, which are quite varied. There's two papers, one that's currently in the referee process and one that I'm only just now collecting data for that I'm going to be talking about. The first one is on the late time analysis of the black hole candidates microlensing events, MACHO-96-BLG-5 and MACHO-98-BLG-6. And the more recent work I'm working on is a physics astronomy education work on the cultural aspects of graduate departments in these programs. So let's start with the science, right? So to begin, let's take a quick look at how microlensing works. So let's say you're observing this yellow background star, which we'll call our source. If an object has mass, as most of them do, let's say this green lens, and it passes in front of that source, the light from the source is going to be amplified due to the mass of the lens, which deflects light rays such that the source emission is effectively magnified, as we see on this plot of brightness versus time below. As the lens continues to pass the source, the amplification decreases and the background star continues to shine at its baseline magnitude. So as it just continues along, the star goes back to normal. From the equations that describe the amplification of a microlensing signal over time, we can see that the amplification is ultimately determined by the geometry of the situation, meaning the distances of the source and the lens, how closely they pass, things like that, as well as the mass of the lens. And note that while a microlensing curve like this is not enough information to determine the mass of the lens specifically, it does show us that a massive lens object exists, whether or not there is any electromagnetic signal from it. So for this reason, a popular application of microlensing is in the detection of isolated stellar mass black holes. This figure from LIGO shows us the mass distribution of known black holes and neutron stars, with neutron stars at the bottom in yellow, an empty region from, well, a mostly empty region from about 2 to 5 solar masses between them, and black holes detected by X-ray binaries, they're in purple. And then finally, the LIGO black holes detected through gravitational waves in blue. An active area of research is this gap in between this 2 to 5 solar mass range. And the question is basically whether or not this gap is a property of stellar evolution, that black holes are just not formed in this mass range, or that this is just a shortcoming of our observations, some kind of selection effect that we're observing. So considering that all known stellar mass black holes, for the most part, except for this, I'm not sure if my cursor is actually pointing, but there's one LIGO detection recently that actually fell in that range. That might have been an isolated stellar mass black hole. But for the most part, we don't understand this population of isolated stellar mass black holes because they're hard to detect, because they're not in binaries, which is generally how we detect black holes. So until we have a sense of the black hole population in this region, this picture is inherently limited by our detection methods. Enter microlensing, the detection method that doesn't need any electromagnetic emission, doesn't need a binary, and is therefore perfect for the detection of isolated black holes. So the two events that I'll be talking about in this work are both from the MACHO survey, which was, designed to look for dark matter candidates in the form of compact objects. MACHO-98-BLG-6 and MACHO-96-BLG-5. You can tell by the title, they were discovered in 1998 and 1996 respectively. And off to the right here, we see the light curves of both of these events. Now, these events have been studied pretty extensively previously. Some of the more notable works are Bennett et al. From 2002, in which they used basically analysis of the light curve data to estimate the mass of the lens and say that, okay, they're both about 6 solar mass black holes. Additional works have come to support or refute that statement, but the thing is, it's difficult to break degeneracies in light curve data. So one way or another, you have to invoke galactic models or statistical assumptions or some kind of not very robust piece of information in order to say anything one way or another. But luckily for us, we live in the future, meaning 20 years-ish have passed since these events, which means that there's a whole bunch more data to work with. So what I have, in addition to the light curves of the events, are high-resolution near-infrared images from Keck, from the NERC-2 instrument that I took in 2016 and 2017. There's Gaia data for one of these targets, and there are archival HST images for both of these events fields in several filters shortly after the peak magnification of the event. And most importantly for what I'm trying to do here, the fact that 20 years have passed means that whatever proper motion existed between these two lens and source objects should have separated the two objects enough by now that we can resolve them, meaning that if there is a lens that is something that is not a black hole, we should be able to see it. So the question I'm trying to answer in this work is, can we see a lens? So how do we do this? I'm going to kind of step through it with one of my events. So this is a Keck NERC-2 AO image from, I think this one is from 2016. And basically what we do, so this central circled guy in green is the source of the event. So when I say source, that's the background star that was magnified by a lens, whatever that lens may be. So what we do is we say, okay, here's the image. Here's a bunch of bright stars in that image that we can use to reconstruct the PSF of our detector. We use that PSF to find all sources in the image. And then we're going to look close in nearby the source, the target source, and see if there's anything there, any of these sources close in this range of in which a lens might have traveled since the microlensing event, and see if there's anything there that wasn't there 20 years ago. So there's the residual for that image, and we can see here in this HST image from, oh, my little window is blocking I think it's 2000, but I can't read it because everybody's videos are in front of it. But from the past, and we can see that the same set of stars are there, meaning that no new object has popped up in the time between the event and now, which, I might just say, okay, no new sources, must be a black hole. Thank you for coming to my talk. But of course, it's not actually that simple. We have to think about how robust our detection is, right? So I'm kind of skipping over a few steps here, but basically by using a combination of, planting stars into the image, using that PSF that we generated to plant artificial stars into the image, and then trying to identify them, we can determine what our completeness is, basically given a position on the image and a star magnitude, what fraction of the time do we find that star? And then by using synthetic isochrones, we can map that magnitude and distance limit into a parameter space that is more useful for microlensing. So these two figures here are showing the detection limits of our images for each of these events, because they have slightly different fields, projected into from radial offset and magnitude space into relative proper motion on the y-axis, lens distance on the x-axis, and lens mass in color. So what this is basically saying, for a lens mass and a relative proper motion between the source and lens, what is the minimum mass that we wouldn't be able to detect? What masses below would our images have not identified an object? Now, this image right now doesn't say anything about the actual microlensing event. This is just a statement of how well our camera is working, right? But we can add these curves, which come from the light curve. Basically, we fit that light curve to models. And from that model, though we can't define a lens distance specifically or a relative proper motion specifically, there is a relationship that comes between those two parameters. So these bands, in each case, there are two solutions for each event, show the parameter space allowed by our microlensing light curve fits. So basically, we have to say within these very narrow bands, what is the minimum mass that we wouldn't have been able to detect? And in either case, no lens mass is allowed above 0.55 solar masses for a luminous lens, for a star, right? It could be a greater mass object that had no light that could obviously not be detected, but a star would have to be below 0.55 solar masses for us not to have seen it. So there's one, actually I'm gonna come back to that. So we can take that same set of parameters that come out of our light curve fit and examine a second solution, a second relationship. And this relationship is that of the lens mass as a function of the relative proper motion between the source and lens. So top figure, we were already looking at it. Bottom figure, for each of those events and for each of the two solutions that came out of each event, what is the relationship between the lens of the mass of the lens and the relative proper motion, right? And that's what we see in those green and blue curves. Now, the shaded region at the bottom is marking off masses below 0.55 solar masses, which, as I just said, is the limit below which we wouldn't have detected. So we can see that in basically all cases, except for the gray region to the side, which I'll get back to in a second, in all cases outside of that, the range of masses allowed by the light curve fit are well above the minimum mass threshold of our detection limit. So for almost all parameter space, and I'll get to that almost, there is no possible stellar lens that we wouldn't have seen that could have caused this event. Now you might be wondering, what's that tiny bit of parameter space that I haven't eliminated yet? If we look at the bottom gray region on these two top figures, right? The region of relative proper motion below 2.5 milliarcseconds per year. What that means basically is that the lens and source still, all these years later, have not moved enough for us to resolve them. And that corresponds to this same gray bar on the left in the bottom two figures. So in those gray regions, because the lens and source might still be on top of each other, we wouldn't have been able to detect a star anyways, right? Because it's caught up in the PSF of the source. So what can we do there? And I'll have to go through this part quickly so I can get to paper two. But basically, to explore this possibility, I developed this new method of examining microlensing events that I ambiguously refer to as lens flux analysis. So this involves combining different types of data, primarily a microlensing light curve with an image of the source in the same filter as the light curve. So in short, the light curve fit yields a parameter that we call the blend source flux fraction, which is basically the percentage of flux in the light curve aperture to come from the source star as opposed to the lens or neighboring stars in the atmosphere, or not atmosphere, in the aperture. Separately from the images where we assume that the source and the lens are unresolved, I explicitly measure the flux from the combined source lens object, or target as I'll refer to it, and the total flux that would be collected by the MACHO light curve aperture. So with some rearranging, these quantities can be combined to yield the flux from the lens in a process of elimination sort of way, right? If it's not coming from the source, or if it's not coming from the neighbors, whatever's left has to be the lens. So the plots here show, based on our images, what the source and lens magnitudes would be as a function of this blend source flux fraction, with the lens in the solid yellow line and the source in the dashed cyan line. The white regions off to the right indicate values of the blend source flux fraction for which there would be no lens flux, meaning a non-luminous lens, kind of like a black hole. The vertical lines are the blend flux values to come from our light curve fits for the two different solutions. And you can see that in the case of M96-B5, there are two solutions that potentially allow for lens flux, for a luminous lens. But in the case of MACHO-98-B6, the solution is pretty firmly in the range of zero lens flux, though the error bar does extend into a potentially luminous lens. So we use that as a lower limit, basically on the flux of the lens. So this whole analysis spits out basically a separate source and lens magnitude, right? And we have this analysis in two different filters. In addition to this separate source and lens in two different filters, we have two additional filters of the combined target. So what I do with that is basically try to see if we can match the SEDs that come out of this analysis to synthetic isochrones. So I'm basically searching through like a library of artificial stars to see whether these objects match up to either a single object or two unresolved objects. So the first column is pretending that the target we're looking at is only one star and seeing if we can fit that blob, potentially one or two objects, to a single star. And we get pretty decent fits there. And then the second two columns are, okay, instead of a single object, we separated the source and the lens in two filters, and we have the combined target in 4 filters. So let's kind of try to fit that whole mess to 2 different objects. And we find we search for the best combination fit, right? So in each of these cases, we find potentially good fits. We can find objects that fit the photometry for either a single object or a double object, which seems like it's a pretty ambiguous result, right? We haven't really said anything one way or another. But the nice thing is that we can put these potential lens objects in the context of a figure it's related to the figure I was showing earlier. These figures here, instead of mass lens as a function of relative proper motion, are mass lens as a function of lens distance. And note that in each case, the curve assumes a source distance that is the source distance of the match. So for each of these matches, we plug in a source distance, we get a curve, and then over the curve in the white lines, I plot the lens distance and the lens mass of the match. And again, remember that the band in blue or green for each of the 2 solutions is the allowed range of lens masses by the light curve. And in each of these cases, though the photometry can be found to match, the lens that is resulted from that match is not in a range of masses allowed by the light curve data. So again, though you can kind of try to convince yourself that you see a second star, I can't find a second star that has a mass that is allowed by the light curve. So in the paper that I wrote on this, that it should be coming out shortly, I go through a couple more bits and pieces of how we can eliminate how we can use different pieces of information to eliminate the possibility of a blended source. But in terms of things I can say for absolute certain, I think the best way is to break it into two regimes to express the results. And that is the regime of low proper motion and high proper motion. So high proper motion, in either case, we have some limit for 96-BLG-5, it's 0.17 milli-arc-seconds per year, and for 98-BLG-6, I can't see the number I have there because our videos are in the way, but whatever number it says there, above those relative proper motions, no object is possible to be the lens except for a black hole, definitely. Below these proper motions, it's a little bit more ambiguous. We've done this photometric analysis to try to eliminate the possibility of a stellar lens, which, as you can see in those previous figures, we can't find a stellar lens that fits the microlensing geometry. However, I would be remiss if I didn't mention that there are potential other things in space that it could be. It could be a neutron star. MACHO-98-BLG-6 was actually followed up by X-ray observations, and the observations found not enough flux to be consistent with a neutron star. So it's not likely in that case, but it could still be the case for MACHO-96-BLG-5. They could be white dwarfs. They could be brown dwarfs. The analysis I did was specifically only looking for stellar lenses. So there's still some ambiguity. I can't entirely say that both of these objects are black holes. However, we have, I think, pretty confidently eliminated the potential of the lenses being stars. So with that, I'm going to hugely switch gears into something completely unrelated. Actually, I don't want to say it's completely unrelated, but initially seems extremely unrelated. So the most recent part of my thesis that I've been working on, which will constitute the last chapter of my thesis, is a project on culture and equity, which I know are things we're all very interested in these days. So just to start off, what is culture, right? What do I mean when I say that? Culture is a system of inherited values, goals, and language that provides members of a group with a shared sense of who they are and a common purpose for action. You can think of culture as what is done, how it is done, and who's doing it, right? There are many ways in which a culture can demonstrate its shared values, including, but not limited to, how it defines its goals, how it evaluates and socializes people, how decisions are prioritized, and what expectations group members, especially leaders, have. So this is where I want to do the breakout groups. Hopefully I can, or maybe Angela, it's best if you do it. I want you to put everybody, not including me, into breakout rooms of like 3 to 4 randomly. And in these breakout rooms, we'll just be there for like 3-ish minutes maybe. I want you to discuss what you think the culture of academic astrophysics is. Like, I want a description of the culture that we work in. What is that culture like? What are its characteristics? What are its values? So.
All right, I'm gonna try it. And then you should have the power to bring us back.
So our discussion in breakout room 3, I guess, maybe, I don't know if that was the number, I think can be summarized in terms of that the academic culture tends to be a little bit elitist and has a pretty narrow-minded definition of success, even though, and a narrow-minded definition of like what is a worthy pursuit of your time. But that being said, the academic astrophysics culture in some ways is a little bit less of that than the academic, just pure physics culture, because there's a bit more of an emphasis on outreach within the astrophysics community.
Interesting.
So can breakout room 2 piggyback off that?
Go ahead.
So we were talking about how astrophysics, as with all science, likes to tell itself that it is objective and based on merit. However, it exists in a system that has a lot of oppressive structures, and people inherently are not objective. And as a result, it ends up varying and having these very often less obvious, often very obvious, but sometimes less obvious manifestations of these structures. And as Catherine was saying, because astrophysics is a little bit better than physics about this stuff, it pats itself on its back when really most of what astrophysics does is say, we see you, we hear you, and when it says, can you maybe get rid of the barriers? It says, no, but we do see and hear them. And
Yeah.
so I would say that's a lot of.
So that leads actually really well into kind of where I'm going with this. So there's 3 bits of culture that I'm really gonna focus in on. So from, you know, literature review on education and culture in both physics and astronomy, 2 beliefs stand out as being fundamental to the culture. First, that of meritocracy, by which opportunities are believed to be distributed on the basis of individual effort, talent, and achievement, rather than by heredity or privilege. And second, like you said, Hannelore, objectivity, which positions impartiality and a focus on evidence as taking precedence over personal preference or feeling. And there's a third kind of meta belief that I find to be particularly interesting, and that's the often held idea that physics or astronomy is somehow devoid of culture. And the physics and astronomy communities are just a bunch of perfectly rational actors, not subject to the effects of socialization, immune to the impact of the society at large. And this idea is examined in the anthropologic study of Sharon Chweik in her 1988 book that is basically it's literally like an anthropological study of physicists. And she does this study in labs across the US, Europe, and Japan. And she notes that most physicists would argue that there are no cultural influences on their activities as scientists. And it's the reason I ask this question to you as a group is because I recently had the experience of, I ran like an anti-racism reading book club thing in my department, which was really lovely. Lots of great discussions from all the department members to come out of that. But it was an interesting moment at one point when we were discussing basically cultural racism, which is when cultural behaviors, aesthetics, whatever, are kind of used as a proxy to discriminate against race, if that makes sense. So I'm not racist, I'm just saying this culture has a bad influence, and it's basically a tracer for race. So we were talking about cultural racism, and everybody's talking about how we want to fight cultural racism. And I kind of hit pause on the conversation and I asked, if we don't want to impose our culture onto other people, do we understand what our culture is? Like, can anybody describe what our culture is? And it was total silence. Nobody had an answer. Nobody could say what our culture that we need to make sure we don't impose is. And I feel like this is very consistent with that idea that Chweik states here, that physicists and scientists at large can often not identify the culture that they exist within, thinking it just kind of doesn't exist. And that's, you know, an idea. But, you know, if we look at data here, this is showing basically for different STEM fields, the fraction of bachelor's degrees, master's degrees, and PhDs that are awarded to either women or underrepresented minorities. And we can see that very clearly that this concept of complete lack of a culture is inconsistent with this clearly inequitable picture of the, you know, just extremely low numbers, increasingly as you get further and further in academia, of minoritized people being awarded degrees. And, you know, I feel like we have a tendency to say astronomy is a little bit better than physics, but when it comes to racial equity, it's actually the worst of the STEM fields, which I think some people are kind of surprised to see. So from data like these, we can see that our cultural beliefs of meritocracy and objectivity and culturelessness are inconsistent with a clearly inequitable reality, right? So revisiting these ideas, and though perhaps logical sounding at first, meritocracy incorrectly assumes equal initial conditions. As Carlone Johnson notes in her 2007 work on the science identities of women of color in STEM, belief in meritocracy of science made the way that some laboratories were divided by race and ethnicity seem like a matter of choice, as data like those in the last slide are sometimes interpreted. Further, the belief in objectivity not only ignores the limits of human cognitive ability, but as Maria Ong explains in her 2005 work on the body projects of women of color in physics, historical studies about the gendered nature of Western science suggest that founders of the modern university deliberately associated masculinity with the qualities of rigorous intellectual inquiry and objectivity, and associated femininity with emotion and subjectivity. So in this way, both of these faulty beliefs are shrouded by the implicit insistence that physics and astronomy are culturally neutral, rather than largely reflecting a specific subset of Eurocentric and masculist norms, the way most of academia and most of society does. This issue is perfectly described by Simone Hyder-Adams' 2019 work, Deconstructing the Identity of Black Physicists, in which she says, I'm not going to be able to read this because the bubble. A leading ideology that we see as harmful in physics culture is the idea that physics sits independently from our broader culture, and that it is not influenced by the systems of oppression and marginalization inherent in society, i.e. sexism, racism, homophobia, transphobia, and ableism. The spreading of this ideology is harmful to Black physicists, who know from personal experience that the racism that they encounter daily does not disappear in physics spaces. It is in fact amplified at times because of the collective denial perpetuated by the community's belief that physics is without culture. When one experiences discrimination, they are often questioning if it is truly that, and when those people are denied by the community, the fault falls back on the person being victimized. So what does this leave us with? If we can't identify the culture of physics or astronomy, we cannot see where our criteria for excellence or ability are influenced by our cultural expectations, thereby excluding culturally different groups. We cannot see where neutral judgments are a proxy for discrimination on the basis of identities like gender or race. And we cannot see where our culturally derived practices are being exclusionary to those with different backgrounds. And these glaring blind spots in our self-awareness as a community lead me directly to the question I'm trying to solve in this project I'm now conducting. So, what do I want to know? My fundamental research question here is, how do female and non-binary people of color perceive the culture of physics and astronomy departments while in grad school? And importantly, how do they perceive their own fit within that culture? Additionally, and most productively, I want to understand what aspects specifically of that culture in these departments poses challenge for such people while in grad school. So that is, what problems do they identify? What strategies do they employ to navigate said challenges? What challenges can't be overcome? And how do they think we could prevent such challenges? I have many goals in doing this. Intellectually, I think it's an interesting question, right? We see all this data showing the inequity and we come up with various reasons, but I am curious to understand what exactly it is about academia, graduate school, that make departments sometimes such a, I don't want to, how do I say this diplomatically, that create problems in retention of minoritized students, let's say. As a practical goal, I think that this work is going to help inform physics and astronomy graduate programs to better support students with minoritized identities, which is a thing I think we're all very interested in right now. And personally, I have to say that I'm kind of curious of the extent to which my experiences in graduate school are similar to those of others with similar identities. Yeah, so how am I doing on time? I'm going to just say one more thing for now. And that's kind of, what is the theoretical justification for approaching this problem the way that I'm approaching it? So there's two kind of bodies of work that I'm basing this project on. The first is feminist standpoint theory, which is telling us that basically to understand and ultimately to remedy issues of inequity, we should start with the lived experiences of those who are likely to have been treated inequitably. And this begs the question, who are those most likely to be treated inequitably, right? So piece one, we want to fix issues of inclusion, we ask those who aren't included, they know best. To answer who are those who are most not included, oh no, my battery's about to die. Or rather, least included. Let me get my charger, it's right here. So to answer that question of who do we turn to understand the inequity, I am referring to ideas from Black feminist thought, which tells us that the paradigm of sex discrimination tends to be based on the experiences of white women, while the model of race discrimination tends to be based on the experiences of the most privileged Blacks. So the experience of being a woman of color allows for a particular understanding of their position in relation to both sexism, racism, as well as additionally potentially classism. So by being positioned at the intersection of multiple axes of oppression, I suppose, women of color have a heightened understanding of the way these systems work, the way they interact, and the way they affect people. So rather than separate our understanding by first interviewing, women, and then maybe interviewing people of minoritized identities, which is how a lot of this research has been done before, I'm trying to look at it all at once, see how it all fits together. So the way I am approaching this work is literally doing just that. I have a population of women and non-binary people of color, mostly underrepresented ethnic minorities, as well as people who are underrepresented along other axes, like orientation, gender identity, religious identity, things like that. And I'm going to ask them. I'm going to ask them about their experiences. I'm about halfway through interviews right now, actually. And it's been a fascinating process to hear from so many people who really are the furthest outside of the culture, describing how they experience it, what they observe, how they understand it to work. And I expect results to be published sometime this summer. Being that I'm supposedly graduating in May, and this is part of my thesis. And I really look forward to being able to share those results. But I think that is all I have for you now. So thank you for listening, and it's not a joke this time. And I'm happy to take any questions.
First, let's give Fatima a round of applause, everyone. Unmute yourself.
Thank you.
My dog even appreciated the talk.